Hi, I'm recording this video for MATH662, and I thought it would be a good idea to go through the Julia tutorial in a video, and then you guys can watch that and go through the tutorial yourself on your own time. And that way we can have more time to do other things. So let's have a look here. Okay, so everyone has been able to install Jupyter and download the Julia tutorials, and then we started going through the introductory tutorials here. So we went into introductory tutorials and intro to Julia, and then the short version. This is the tutorial we were going through in class, and let me know if you have any difficulty opening up Julia and getting it to this point. But I think everyone was able to do this, no problem. Okay. We did go through this notebook in class, but I'll just record this as well. Just go through this very quickly. Okay, just waiting for the kernel to start. So very often when I use Jupyter notebooks, in order to have some extra screen real estate, I'll go to this view menu here and I'll toggle the header to get rid of that, and also toggle the toolbar as well. And that just gives more space, especially when presenting this in class on a projector or something, or recording a video like this. It just gives more space. And let me just see if this is a good zoom level. Okay, that's a little bit too much, so I'll put it back. So hopefully this is easy to read on everyone's screen. So it says running a cell, you want to hit Shift Enter to run a cell. We already did this actually. Let me just restart and clear output. And maybe I will keep the toolbar up. The toolbar is a little bit helpful. You notice when I'm on this cell, it says Markdown, and when I'm on this cell, it says it's a code cell. So that's one thing that's useful in the toolbar. I usually don't use this functionality up here. Instead, you'll see me sort of moving around without using my mouse, because there are a lot of keyboard shortcuts that are available in Jupyter Notebooks. If you press the H button, for example, I wonder if question mark works too. Let me just try question mark. So if I hit question mark, no. So it has to be H. So if you press H, that'll bring up the keyboard shortcuts. And the keyboard shortcuts that I like, so one is to know about these two different modes. There's the command mode. You press escape to go into command mode. And you can press enter to go into edit mode. Let's see what other ones I use here. F for find and replace, that sounds useful. Let's see what else. So there's the shift enter to run a cell and then select the next cell below that. Or if you want to just run one cell, then you can do, on a Mac it's command enter, but on a Windows it'll probably say control enter instead. Y you can use to change a cell to a code cell, and M will change a cell to a markdown cell. Let's see, what else is there that I like to use? Up and down to move from one cell to another. And also J and K. So K is to go up and J is to go down. I actually Well, I use both of these. So sometimes I use arrows, sometimes I use JK to move up and down. And let's see here. Cut, copy, and paste. Those are useful. So it's just what you would expect. DD is to delete a cell. If you want to merge cells together, you can hit Shift M, and that will merge a cell with the cell below. Or if you have multiple cells selected, it will merge them together. Command S to save, and checkpoint. So that's an important thing, is when you're saving, you're actually creating a checkpoint. So it's always kind of saving. You don't have to save. You never have to worry about losing your work. But if you want to create a checkpoint, you can do Command S, and then you can make a bunch of changes. You like, I didn't like that, and you can go back to the checkpoint. So that's what is useful there. L is to toggle line numbers. Often it's useful to know what the line numbers are in a code cell to find, where things are going wrong. If you get an error message, it'll refer to a line number. So that's very useful to have on. Let's see what else. If the kernel is kind of frozen, you want to stop some calculation you're doing, you can hit II, and that will interrupt the kernel. And if you want to just restart the kernel completely, then you can hit 00. Yeah, so those are a bunch of the commands that I'll be using to move around. And these are, when you're in edit mode, when you're actually writing code or writing markdown, then these are the keyboard shortcuts that are available there. But these are like the normal keyboard shortcuts that you would have in any editor on your computer. Okay, let's continue. So I'm just pressing down to move up and down to move up and down here. And if I hit enter, then that will allow me to edit this markdown cell. And then if I hit command enter, then it renders it. It makes it look nice. So you can see this like shift and enter are this different font, and that's created by using backticks around shift and enter. Okay, shift enter to run this, and it will print by default when you execute a cell. It'll be the last thing that gets executed. It gets printed. If you want to suppress the this execution or this output, then you can put a semicolon, and that will suppress the output. And to get help for Julia function, you can put a question mark in front of the Julia function, and this will display the help. There it is. So there's the help on using the print line command and some examples. And if you want to use shell commands, you can use a semicolon. So that lists the files in the current directory, and the current directory I am in is on my computer. It's this one. Okay. Let's close that. And we'll open the next notebook. And I think I'm going to, again, clear the output here because we were working on it before. I'm going to clear the output, and we don't have to, we can go through it again. All right, well, while we're waiting for this, you can see how you can create a bullet list in Markdown. You just put a dash and a space, and then that will create a bullet list. So okay, Command Enter, you can see what that looks like. Is it still, wait, let me do that again. Restart and clear output. I can see that it still has the output here from the last time. Is it running? Oh, there, okay, it's restarting now. Okay, all right, we're good, okay. Oh, and it actually ran, that's weird, it output twice. Okay, well, let me just run that. Huh, that's really weird. That is really weird. I'm gonna restart and clear output again, and I will pause while I wait for this. Okay, we're back. Okay, let's run this. So we're gonna set the variable string 1 to how many cats, and string 2 is this one. If we just print string 1, we get that. And if you want to print string 1 and string 2, you can list them like this. You can also add other things here. So 10, and it just merges that together. Even though this 10 is an integer, it just adds that into the string as well. Maybe I want a space. I can do that to just insert a space because I don't want that 10 right next to that question mark. Run that there, now there's a space in there as well. Okay, let's run this one. So here's how you can use emoji to, as a variable. You can use a lot of different symbols in Julia, and we'll get into some of those in a bit. I'm actually not sure how to insert such a emoji. Do I do colon, smile, colon? Does that work? No. Not sure how to do that. I'm not sure how to get those emoji in there. But there's other math symbols that we can use, like you can put alpha and then hit tab. And that'll work. Or maybe it's, oh no, that's not what I want. Anyway. Okay, 1 second. All right, okay, I just had to close my window and open the blind. But I also looked up how to input these emojis. I just Googled it, and I found this list on the Julia docs, and they show you how to enter these emojis. So the one that they entered there is this one. Let's try that. So I'll just create a cell above by hitting A, change it to Markdown with hitting M, and then I will try this smile, and then I'll hit, oh, actually, 1 second. Let me go back to a code cell. Yeah, let's do it in a code cell. So smile, tab. Okay, so I typed in SMLIL, and I hit tab, and we see all the different possible choices. So we can do smile, and then hit tab again, and then hit enter. And we can do smile cat, and hit tab again, enter. Okay, so that's how you enter these emoji. I mean, I obviously don't use them very much, but that's where they are. And you can use these as well in Markdown. Let me try that again in Markdown. Let's see if I can get this to work. So in Markdown, smile colon. Let me do Okay, no, that didn't work. Let's try that. No, okay, I'm not sure how to do it in Markdown. To be determined. But for now, I know you could simply copy paste, for example. So I could actually grab this one and then paste it in here like that. So that's a way to, if you want to get these into your Markdown as well. Okay, moving on. Yeah, so we can use these emoji as variables. You can use emoji just wherever you like. And it's definitely useful for like the fact that it's Julia supports Unicode means that we can now use all of the Greek letters directly in our code, which is actually very, very useful. Instead of having to spell out the word alpha, you can actually have the alpha symbol there. And it makes the code look more like the mathematics that you're writing down on paper. Okay, we went through this last time. Tuples are, so these are ordered tuples. So you can write them like this, and you can refer to the entries of the tuples like this, but tuples cannot be modified. They are what's called immutable, so that this is an immutable data structure, and that's why we have this error. If it's an array, later on we'll see arrays, and arrays are immutable, so you can actually change arrays, but not tuples. And that's somehow actually, in some cases, tuples will be the correct choice because they will be faster because of this immutability makes it so that you can work with them faster in some situations. Dictionaries can be used to have kind of like a database where you can refer to the entries of this dictionary with the keys instead of always just having to use integers like you did with tuples. You can now get the information from this with a key. Okay, arrays are entered with square brackets. So here's an array of strings. Here's an array of integers. And here's a mixture of integers and strings. And this is not a great idea because the Julia does not know what the type of the objects are in here. So it just says that it's any, and that can cause your code to run slowly. So this is not a good idea to have an array of mixed types like that. Here's an array of arrays. So you can see this is a one-dimensional array of one-dimensional arrays of integers. And here is a 4x3, sorry, a two-dimensional array. It's a 4x3 array of float 64. Okay, for loops. Oh yeah, I think I typed this in last time just to show you what is this 1:n. So 1:n is a shortened form of the list of integers from 1 to 10. Okay, while loops. So while loops look like this, very simple. So we were just playing with this last time. If statements, so it's if, else, and then you always need the end for an if statement. So there's an if, else, end. We can also use this ternary operator, question mark colon, to be a short version of that. If, else, yeah, if, else. So if this is true, then return X, else return Y. Yeah. Okay, this is where we left off last time. Functions in Julia. Very simple function here. So you use the word function and end to create a function. So function f of f is going to return the last value in the function gets returned automatically. So you don't need to say the return keyword. So you could write return here, and that would do the same thing, but you don't have to. It will return the last thing in the function by default. Okay, so I ran this and it created a generic function with one method. Another way to create a function is this short way. You can just say f of 2 of x is equal to x squared. And you can also make it as an anonymous function. So f3 is the function which takes an input x and maps it to x squared, or takes input x and returns x squared. I especially like these last two because they are very much the way we would write things on the board mathematically. Let's call these functions. So f of 42 is 42 squared. And you see they all do this, they all do the same thing. So the nice thing about Julia is you don't actually have to explicitly indicate the types of things. Everything in Julia has a type, but you don't have to, when you write a function, say that what the types of all the variables are. Julia can take the types of the objects that you're calling the function with, and they can sort of determine the types of everything in the function, and then that allows it to compile down to very efficient code. So let's have a look at this. That function up there, we just ran it on an integer, but actually it works just as well if you give it a matrix. And what happens when you run a function in Julia on a different type, it'll actually compile another version of that function that is efficient with this type. So you see that there's a bit of a time delay there when I ran it the first time. That's because it had to compile the function first, but if I run it again, it's much faster. And you can sort of see this if I put @time in front of this. We can see that that was very fast. I'm just trying to think of a quick way that we could demonstrate this. Well, we'll see it later. Next time we come to a function where it's going to compile, I'll time it, and then we'll run it again. And you'll see that the second time it runs, it's much faster because it just runs the compiled version that it's cached. Okay. On the other hand, we're not going to be able to. Well, here's a good example actually. So let's just time this. You'll see that I think it's going to have to compile. Let's just see. Well, it gives an error, so maybe that was not so useful. Yeah. So the point is here that this function actually won't work with vectors because v squared, multiplying a vector by itself, is not defined mathematically. And so in this case, it gives an error message. And the error message is just saying that this power function there's no method matching, giving it a one-dimensional array of floats and an exponent of, which is an integer. It's not defined. There's no method that will do that for us. Functions, not only can they take input and return output, but they can also mutate an input as well. For example, let's just define this vector v of integers, and we can run the function sort on that, and you see it returns the sorted array. However, it did not change the original array itself. So the original array is still the same. It created a new array and returned that new array, which was a sorted version of V. However, sometimes we actually just want the vector V to be sorted, and we don't want to create a new array, which would allocate extra memory. So to avoid that, we can run this function sort with an exclamation point. These exclamation point functions, this is by convention in Julia a way to indicate to somebody that this function is going to change the input. It's not required to do this. It's just a nice thing to do to so that people aren't surprised about why things are acting the way they are. So that's what that exclamation point is there. And now we'll see that the vector V has actually been sorted itself. And let's just put an @time in front of this. And you'll see that when we run this function, it does actually have to allocate some memory. So it allocated, not sure exactly why it's 112 bytes, but it allocated memory for this array that it returned here. If we do the same thing with the sort in place, you'll see that it did not do any allocation at all. So no allocation occurred here. It just sorted it in place. Okay. If we do want to apply a function to each entry of an array, we can do it this way. There's a map function that works like this. So our function f, remember, it's squaring things. So now we're applying f to each entry of the array in this way. You can also do it with an anonymous function like this. So you can just put an anonymous function in there to cube every entry of an array. Another way to do this is with the broadcast function, which is similar to map. And it's exactly the same as calling the function with a period. And this is actually my preferred way of doing it. You'll see this dot notation used quite a bit in Julia. So if you want to apply the function to each entry of an array, you just put f dot, and this will call this broadcast function. So instead of typing the word broadcast, you can instead just put f dot. So for example, if we were to call, we know f of a is going to do the standard matrix multiplication. So that'll be a times a as a matrix right there. And on the other hand, if you instead want to square each entry of the matrix, you don't want actually the matrix multiplication, you can do f dot of a, and that will square the entries of a rather than doing a times a as matrices. So this dot notation gets used all over the place. So in this example, what's going to happen here, I guess we'll start here. It'll do this first. So it'll apply f to each entry of a, and then it will multiply each entry of that by 2. So you see the dot multiply. And then it will take this thing and it will divide each entry of this by each entry of this component-wise. And finally, it will add component-wise this array with this array. Some of these dots don't actually need to be there. So I'm pretty sure I can delete this dot here and this dot as well, because those mean the same thing. However, doing this dot divide is required in order to say I'm going to take this array and divide it by this array component-wise. So you do need the dot in that case. So let's see if I, let me just copy paste this here and then undo just to check, run this like that. And yeah, it returns the same thing. Okay, and that just means exactly the same thing as this, where you can create a broadcast function with an anonymous array and act on this array like that. And that will give the same thing. All right. Now I will close this. If maybe I guess I could create a checkpoint. Close this down. And let's go on to linear algebra. Okay, back now. All right, here's linear algebra in Julia. Here's how we can get a random matrix of integers from 1 to 4. So normally if you just call rand, it defaults to float 64. But you can actually specify any kind of collection here of objects in order to take random elements from that collection instead. Guess you could look at the rand documentation to see how this rand function works. I think it's kind of long. Let's see. So it says pick at random element of an array or array of random elements from the set of values specified by S. So that's what that is. So you can specify a set S to pick your random numbers, or you can specify a type as well. You can, but by default, it defaults to float 64. So for example, if you want random integers instead of float 64, you can put int there and it'll give you random integers. And yeah, good. All right, so lots of information in the documentation there. Here's how you can create a vector of ones. You can fill, you can use the fill, so you can take this value and fill an array of size 3, a one-dimensional array of size 3. Another way to do this is you can say you can just use the ones command. So you can say ones of 3, and that will give you the same thing. So this fill 1 3 is the same as saying give me the all ones array with 3 entries. All right, one of the nice things about Julia, and they got this actually from MATLAB. MATLAB started with this, is you can take an array and a two-dimensional array like a matrix, and you can just multiply it by a vector, and it'll do the matrix vector multiplication as you would expect. This is really nice because it looks exactly like what we would write on the board mathematically. The transpose there's a shortcut for transpose in Julia. It's A with an apostrophe, and that will give you the transpose. Let me just show you the A matrix again. So there's A, and you can see that A tick is giving us the transpose. So the first row here is the first column of A. The second row is the second column of A, and the third row is the third column of A. Another way to do it is with this, the transpose function, but I definitely prefer this one because it's much shorter. 1 second. It looks like my dog wants to go out. I will be right back. Okay, I'm back. All right. Where were we? So one nice thing I like about the transpose, if you want to do A transpose A, you can actually omit the multiplication. So that's the same thing as doing A times A like this. So you'll see you get the same thing, but it's nice. It looks a little bit nicer, I think, without having that multiply there. So I definitely prefer this notation whenever possible. And if you want to solve a linear system, this is actually coming from MATLAB notation. So it's A\B, and that is going to solve the linear system for X. Yeah, remember that's what X was. X was the vector of all ones, and we define B to be A times X. So when we solve it, we get the value X back. Great. Oh, my dog wants to now come in once. All right. Yeah, if you want to see my dog, this is my dog right here. So this is Chana. Let's see. Yeah. So this is Chana. She is our oldest dog, and we got her when I was in my first year as a PhD student, and she went with us to France, and then back to Vancouver, and then she drove with us from Vancouver to DeKalb. Yeah, she's a great dog. All right, let's put her here. She usually sleeps under my desk. Okay, so go ahead, go under the desk. So a really nice thing about Julia is that you can take advantage of different types of matrices. So what kind of matrix it is very often leads to different, more efficient algorithms. So let's take a very large matrix here. We're not going to print it out because it's 1,000 by 1,000. I mean, it wouldn't be terrible to print it out. I'll show you what happens. So it's not going to print every entry. Ooh, it's not the nicest. Let me zoom out a bit. So it's a little bit nice the way Julia prints out these large arrays. It'll show you like the top left, top right, bottom left, and bottom right corners, and it'll just put these dots in between. So it won't completely fill your screen with all of the 1,000 by, well, that would be 1,000,000 numbers, right? So it's not printing all of them. But yeah, let's put a semicolon there because we don't really need to see that. And here we're going to do A plus A transpose, and of course that will create a symmetric array, and we can say, is this a symmetric array? And it says, yes, it is. But sometimes if things are even just slightly not symmetric, so like say we make a copy of A sim and then we just very slightly perturb the 1-2 entry. So now we'll see that the 1-2 entry is that, but the 2-1 entry is going to be what? It's that. So they're almost the same. You see, this is 6913 and this is 6925. So very, very close, but not exactly the same. And now if you say is symmetric, it says false. So this is symmetric function. It's actually going through the entire array and it's comparing all the ij to the ji components, and they have to be exactly the same. Otherwise, it's not considered symmetric. So you have to be careful with that. But what we can do instead to make sure that it's exactly symmetric and it doesn't have to check all of those entries to see that it is symmetric is we can use this symmetric command, and then it will only look at the let's see, it's going to only look at, so there's two things here. So data is the array, the asym noisy array. That's what that is. I won't print it, but upload is telling us if it's looking at the upper triangular part or the lower triangular part. And in this case, the default is to just look at the upper triangular part. So why is this important? Well, one, now if we were to say, like, you know, is symmetric, what it does is it doesn't actually look at everything. It just says, well, this is a symmetric array. If I print it out here, where I guess I'll say type of a sim. So if I say type of, so its type is symmetric. So, and that's all it cares about. It just says, oh, this is a symmetric type. So yeah, it's symmetric. So it's like, it doesn't have to do any work at all here to do this. So that's a very simple example of why it's good to explicitly say what the structure is. But let's look at computing some eigenvalues and you'll see also the same thing. Now, this is a good point to notice. This is the first time I'm running this function with a sim, which I think is just a two-dimensional array of floats. So it's going to run a little bit slow the first time. So let me just copy paste it and then run again. And you'll see that it's faster the second time, because the first time it had to compile the function. And the second time it was able to just use the compiled version. And you can also see that there's fewer memory allocation that occurred, because there's some memory allocation occurred during the compilation. And this refers to the garbage collection time. So when Julia when you stop referring to some part of memory, then Julia will occasionally from time to time go and deallocate all that stuff that you are no longer referring to. So that's what garbage collection is. Okay, let's run this one. It looks like, let's see, I'm pretty sure that was the compiled version. Let me just copy paste it and just check quickly. Yeah, it is. It is the compiled version. So, so that was actually pretty slow. That was pretty slow. Yeah, because asym noisy is still the same type, so it was able to use the same compiled version. Now this one is of type symmetric. So when I run this, it's going to, I think, well, maybe it didn't have to compile. Well, maybe it did. Maybe it did. Let me run this again. There's some garbage collection there. Time can be a bit finicky. Each time you run it, sometimes it will take different amounts of time. That's why it's usually a good idea to run it many times, and then take the average of those times. You see, each time I run it, it's like a slightly different time. So a way to deal with this is using this package called benchmark tools. And with benchmark tools, we can use this command btime. So it's the benchmark tools time. And in this case, we'll just do the same. In this case, it's going to automatically run the function multiple times, and it will then give us the average of those times. So it's taking a bit longer because it's actually running it more than once. And it kind of determines on by itself how many times to run it. Oh, maybe I should have put the semicolon. So let's run that again. But yeah, as you can see in the conclusion here, using symmetric on this guy, right? So using symmetric and using the symmetrized version of it, it's like much, much faster, right? So this was like 2 seconds and this was only like half a second. So much faster, much, much faster. Also, it's faster than this one here as well. So this should be, I mean, this and this should be exactly the same, but this was faster because it knew ahead of time it was symmetric, and it can take advantage of the matrix was symmetric, that it knew it was symmetric, so it could take advantage of it. Okay, so the B time is 255 milliseconds. So that's a better idea of how much time it takes. So here it's like 422 milliseconds, 490 milliseconds, 510 milliseconds. So, but if you do it many, many times, then it's on average, it'll be this. I just don't see it from my experiment here, but anyway, that's kind of curious. All right, so let's look at a big problem. So one really nice type of matrix is what's called a symmetric tridiagonal matrix. This, let me just show you what it is quickly on a smaller, I'll just copy paste this, but I'll change it to be just a 10 by 10 matrix. And then I don't want to do this. I just want to see the matrix itself. So here's a 10 by 10 symmetric tridiagonal matrix. You see that it has the main diagonal, and then it has one diagonal above and one diagonal below, and that's it. The rest of the matrix is all zeros. And maybe I'll do it a bit smaller so it can print the whole thing. There you go. So that's a nice example. These matrices are very efficient to work with. And what's interesting about this matrix is it's not actually storing it as a 5 by 5 array. It's actually storing just two vectors. It's storing the diagonal vector, and it's storing the off diagonal vector, right? Which only has 4 elements. And that's it. That's all that this thing is storing. It's just storing those two vectors. But when you print it, it says, oh, I know it's a symmetric tridiagonal, so it should look like this. So it's representing a 2-dimensional array, but it's just storing 2 1-dimensional vectors. And this is great. This allows us to do very large let me run this a second time, because I think there might have been some compilation time there. Let me just run that again. Let's see. Yeah, it's a bit faster this time. Yeah. So there you go. We're doing like a 1,000,000 by 1,000,000 array matrix, 1,000,000 by 1,000,000 matrix. I'm not even sure if I could store that in my memory on my computer. I'm a little bit scared to try, especially when I'm recording. It could fill up my memory quite a bit. So, but it's not storing 1,000,000 times 1,000,000 values. Instead, you know, which would be like, I don't even know what to call this number, but you know, that's a lot of zeros there. So it's not storing this many floating point numbers. Instead, it's just storing n plus, you know, n minus 1, right? Store the diagonal, store the off diagonal, and that's a much smaller amount of memory compared to this, right? I guess maybe we could compute how much this is. Let's see, so n squared, and then each floating point number is going to use, it's float 64, so it's using 64 bits. And so that's how many bits it would be. How many bytes would that be? So I would divide that by 8 to get the number of bytes. And then I would divide that by 1024 to get the number of kilobytes. And divide it by 1024 to get the number of megabytes. Whoa. Again, to get the number of gigabytes. Yeah, okay, so it's 7,450 gigabytes, which definitely is more memory than I don't even have this much memory on my my hard disk on this computer. That is a ton of memory. So that's gigabytes, and then this would, I guess, be terabytes. So it's like 7 terabytes if you were to store all n squared numbers. And let's just see how much memory it's actually storing. So n plus n minus 1. And oh, so that's terabytes. This is gigabytes. Okay, megabytes. So it's 15 megabytes. So 15 megabytes. So let's just record this. So this would be 7 terabytes. So more than 7 terabytes to store an n times n matrix. So if it's just a regular matrix, that's how much it would require. But if we want to store, go to markdown mode, if we want to store it as a symmetric tridiagonal matrix, then this is only going to be around 15 megabytes. Yeah, 15 megabytes to store n times n symmetric tridiagonal tridiag symmetric tridiagonal matrix. So this would be if it's just a general matrix, you know, symmetric tridiagonal, no problem. So we can store that. When n is equal to 1,000,000 yeah, all right, I'm gonna save that. All right, so hopefully you get the point. Let's move on. Let's move on. I'll switch to the next notebook. Be right back. Okay, back. So next notebook is the one on packages. So this notebook says actually Julia has 2,000 packages, but I believe this is actually much more. There's a new website which can be I think it's called Julia Hub. Yeah, Julia Hub. So this website actually is a way to browse through all the different packages that Julia has, and let's see if we can find out how many packages. Yeah, so there's actually over 4,000 packages now. So there's a lot of packages, and I don't know what to say. Basically anything you want to do, probably you'll find a package in here that does it. Some of the most popular packages in Julia are the differential equations package. This is part of this scientific machine learning group who has created this differential equations package. JUMP is the Julia's mathematical programming package for mathematical optimization. And this has sort of become state of the art in the mathematical optimization community. So previously, I think optimization people would be using MATLAB, but now more and more people in the community are using JUMP instead. It's a great package. There's a plots package. This is a recent package, which is similar to Jupyter, but it gives you a kind of like a notebook for Julia, and it's getting to be really popular. And so on. There's iJulia. We know about iJulia already. Flux, this is for machine learning. Yeah, lots of great stuff. Okay, so that's where all those packages are. They mentioned these other websites. I'm not sure if this is still a thing or not, but the one to go to now is Julia Hub. So when you add a package in a Jupyter Notebook, you have to do it this way. So at the Julia prompt in the REPL, you can just hit square bracket, it puts you into the package manager. But if you're in the notebook, you actually have to say using package and then do package.add example. So let me run this and you'll see what happens. Okay, it's taking a while, I'll be right back. Okay, there we go. So now it's done. That actually didn't take too long. So it downloaded the package and it added it to your project and manifest files. And it's in this, for me, it's in this .julia directory in my home directory. So that's where it stores all of these packages. Okay, so now that we have the package installed, we can say using example. And the first time that you say using a package, it will have to do this pre-compilation. I guess we saw this already with iJulia when we were all installing iJulia. And this package was actually downloaded from GitHub. So let's have a look at this package on GitHub. And you can see in this example .jl package on GitHub, the file that we're looking at here is in the source directory, and then it's example.jl. So let's just see if I can find that. So go to the source directory, and then there's example.jl. And what is this code doing? So it's a module called example, and it's exporting a couple of different functions. There's a hello function, and there's a do math function. So here's the definition of the hello function. So this is the doc string, which you would get if you said ? hello, it would print that. And we can see that given a string, it prints hello and then that string. And then the do math function takes a number, any number, float or integer or whatever, and it will add 5 to it. So that's what this simple example package does. So it's quite easy to actually write packages like this. You see there's not much involved to it. I guess good packages also have other stuff in them, like some tests. So here's some tests. You can test the package to make sure that everything's working correctly. So make sure that when you say hello Julia, it'll print this or it'll return this. And if you say do math 2.0, that'll be approximately 7.0. I mean, it's going to be exactly equal to it, but that should be good. All right. So there it is. It's all loaded up. And as I mentioned, if you do ? hello, it will print that doc string that we saw in the source. Yeah, there it is. So it printed this doc string. Okay, so let's run this. Let's run this function. And you see you can put any string there and it'll return that. Let's look at another package, colors. Okay, that was faster. And let's load it up using colors. And create a palette of 100 different colors, distinguishable colors, in fact. There you go. So to the human eye, all of these colors are distinguishable. There's no two of them that are indistinguishable. And so as we know, when you say ram 3, 3, it gives a 3 by 3 array of floats. And if we call it with a collection of integers from 1 to 10, it gives us a 3 by 3 random integers from 1 to 10. So what happens if we ask for random selection 3 by 3 from this palette? Well, it will give us, let's see, that. Oh, beautiful. So it's a 3 by 3 array of colors. It's all distinguishable. I mean, to me, these two look very similar, but no, I can see they're different. So pretty cool. And each time you run it, it will give you, you know, a different array. Very nice. So that's the colors package. Very cool. All right. So we're at the end here. I will move on to the next notebook. 1 second. Okay, so we're back. And I loaded this notebook, and then I also ran the first cell because it can take a while sometimes to load up the plots package. It's a very big package, and it can take some time. So be patient with that. Plots is a really nice package that allows you to kind of do a lot of different plots with a variety of different backends. In the past, you know, different backends would have different syntax, but plots allows you to use the same syntax with a variety of different backends. So you can create a plot and you can just change the backend and see what it looks like in a different backend. And we'll see what that looks like. Okay, so let's use this example data. So we have global temperatures and number of pirates. And we'll start with the GR backend. Okay, let's plot it. So this will do a plot of number of pirates versus global temperatures, and this will be a line. And then it'll, on top of that, add a scatter plot. So you can see this exclamation here, and that's actually going to indicates that we want to modify this previous plot rather than creating a brand new scatter plot. So we want these two things to be on top of each other. So this is going to take a little bit of time. So there it is. So let's see what happens, just to show you what happens if we comment this out and run it. We're just going to get the line plot. And if we run it, both of them, then we get the scatter plot on top, which just puts the points there. If I was to remove this exclamation, it's going to run just this, it'll run plot, and then it'll run scatter, and it won't modify the previous plot. It'll just give you just the scatter plot. So that's why that exclamation is there, to say we want the modify plot version. Okay, and let's add some X label, Y label, and a title to this plot. So notice the exclamation again, it's telling us to modify the previous plot. So it just took the previous plot and modified it like that. So now it looks nice. All right. So let's flip it. We're flipping the X axis. So instead of starting at 0 and going up like this, we are starting with large values of X and going down to 0. Okay. You can also do Unicode plots as well. So we'll see what that looks like. Okay, there we go. Got that loaded up. And let's run the same plot commands, but now we're going to be using the Unicode Plots backend. And I guess we can do also the same. Let me just copy paste this here. Oh, okay, that's what it looks like. Let me just zoom out. There we go. So that's the Unicode plot. So if I haven't had any use for this myself, but it's kind of neat that you could actually do plots like just in the Julia REPL if you wanted to plot there in the terminal rather than in this notebook. You can actually have plots, and looks like this. So pretty cool. I wanted to do one more example here where we use the Plotly backend instead. Plotly, well, there's a couple. So Plotly, let's see what that looks like. Okay. All right, and there it is. I guess what's a little bit, what's nice about it is it has this kind of interactivity. So Plotly allows you to be kind of interactive like this. And there's also Plotly JS. I'm actually not sure the difference between these, but I think the JS is for JavaScript. And then let's see what we get there as well. All right, done with that. And yeah, it looks like it's basically the same. So I'm not really sure the difference between Plotly and Plotly JS, but there you go. See how easy it is to get interactive plots, Unicode plots, and just I think my preference is probably GR. I like these GR plots. I think they look quite nice. So that's it. All right, so I'm going to save this, and then I will close and halt, and I'll load up the next notebook. I'll be right back. Okay, next notebook, Julia is fast. Okay, so this notebook is going to show you why people are so interested in Julia. We've already seen that it's a high-level language, just like Python or MATLAB. It's very easy to program in. The syntax is really nice. It's almost like pseudocode, really. And for mathematicians in particular, it really is. The syntax is very similar to the mathematical notation that we're so used to. So that's really nice. But if it was just that, Julia wouldn't be the success that it is. What makes Julia successful is that even though it's a high-level language, it actually performs very fast. Often it will perform close to the speed of C, especially if you follow the sort of performance recommendations in the Julia documentation. They have some suggestions about how to write Julia code that'll make it fast, but let's just see in here, we'll do a simple example of the sum function. So we're going to do this one. You can see how markdown cells can have LaTeX. So there's LaTeX in between $2 double dollar signs, and that will give you so single dollar signs gives you inline, and double dollar signs will give you a display equation. So that's really cool how you can type math in these markdown cells. Okay, so let's get an array of 10 million floating point numbers, float 64, and we'll add them up. So do it again. So you can see that's really quick. Let's just put a @time. Well, I guess we're doing it down there, so maybe I won't. That's just to see that it's working. So now we'll benchmark it. So let's do @time. Okay, I'm just going to run that again. So it's about 0.02 seconds. Yeah. So it sort of depends. So you see each time you run it, it can be kind of like a different amount of time. So we mentioned this before already. The way to do timing in a better way is to use benchmark tools and run the function multiple times and then take the average. Okay, So here is, this is a way you can actually write some C code. Let me just run this as we're talking through this. Julia allows you to very easily wrap the C code and run C functions. And this is just an example. You can do it in different ways, but you can actually just write some C code here and put it in a string. So these triple quotes at the top and bottom, that allows you to like also have new line characters in here as well inside the string. So that's why those triple quotes are used there. And you see what's going to happen here is it will it'll compile this this code onto my computer. Yeah, I think so. It says you have to have GCC installed, which I do. Okay, and then it defines the csum function. So the csum function is actually going to call the compiled version of this function up here, right? You can see this is a very simple sum function. So you start by declaring s to be 0, and then you go through a for loop, and each time you're just adding the next element of this array x, which is a double star. So it's that's a one-dimensional array in C, and then it returns S. So it's, you know, it's you have to also give it the size as well, because C doesn't know what the size of X is, because this is just a pointer. So, all right. So that's it. Since more recently, there's another method called @call, which allows you to you know, do this in a much easier way. Because this looks a little complicated, but it can actually, there's an easier way to do this using @call. All right, so let's run this. You see it does the same thing. It should be exactly the same sum as we had before. Yeah. Oh, it's actually different. Okay. Well, there's a reason why it's different. Actually, it depends on the order that you're adding stuff up in floating points, because of the rounding error that occurs all the time, and that's why we see a slight difference here in the last few digits. Yeah. So that's what's going on there. We'll talk more about this when we talk about floats. But they are approximately true. So this is true. This is true. But you can see they're not exactly true. So that's why we compare them with this isApprox function instead. So isApprox is a way to, you know, it's kind of the safe way to compare floating point numbers, because saying one float is exactly equal to another is not always the best approach. So instead, you just want to say that they're approximately equal. And this function allows you to compare things approximately by specifying a relative tolerance. So it's either going to be, so if it's atol, then it'll be atol. But if atol is positive, then it'll, oh, okay, I see. If atol is positive, then it'll be 0. Otherwise, if atol is 0, then it'll use square root of machine epsilon. And we'll talk about machine epsilon very soon. Anyway, very cool function. You can change the tolerance that you're using in order to compare numbers. All right, so let's benchmark the C code. So we're going to use this @benchmark, which is another one of these functions from the benchmark tools. It gives more information about, like, how many times it ran, what was the average, what was the min, what was the max. So we'll see this happening here. Yeah, so So no memory allocated. Minimum time is about 11 milliseconds, and the maximum was 63 milliseconds. So you see there's a large variation there, and but the mean was 18 milliseconds, and it ran it 272 times. So if we run it again, let's see what we get. I already forgot what we got. I think we got about 18 milliseconds on average. I think that's what it was. Yeah, so in this time it's like about 17. So it's actually pretty consistent. But whereas if you just run at time, then you saw already how inconsistent it can be. So it's much better to do it this way. All right. So the fastest time was 11.3. Let's see. Let's create a dictionary. So we're going to keep track of all of the times in this dictionary. So the C time, the minimum time was this, and let's load up plots, and we're going to use this package called statistics here, and this is in order for us to compute the standard deviation. So that function, it's not in Julia automatically. You have to say using statistics, and I forget if statistics is part of Julia by default, or if you have to add this package. I don't think you have to add it. I think it's in there. It's just not loaded. It'll only load those functions if you actually want them. So that's why we have to actually say using statistics. The same way we did using linear algebra in a previous notebook. So all of that stuff is actually part of the Julia standard library. All right, so what's going on here? It's taking all of the times. So actually this cbench.times, it gives us all of the 295 times. Actually, let's have a look at that quickly. So cbench.times, what do we get? Yeah, so it's a 295 array of all the times measured in, I guess, actually, I don't know what unit this is exactly. Not really sure. But just looking to see if there's information here. Millisecond. Oh, I see. So we're dividing by 10 to the 6 to get the time in milliseconds. All right, so I'm having trouble thinking about what the unit is exactly for this, but anyway. So we're going to get this time in milliseconds, and then we're going to compute the minimum times and the standard deviation, and then we're going to plot a histogram using the plots package. So plots has a histogram function. So we'll do 500 bins histogram with those values in this array, and then this is just getting a nice x limits and then some labels. So x label is milliseconds, y label is count, and then not exactly sure what that's about. I don't know. All right. I guess we can test it. So let's just test. Let's see what happens. Oh, okay, I see. So label is this legend up here. Okay. So if I clear that, it actually doesn't even print the legend then. So that's a way to get rid of the legend. All right, that's cool. All right, so yeah, you see the amount of variation there is here in milliseconds. It's going down from like less than 12 milliseconds to more than 16 milliseconds. So huge variation, huge variation. All right, so let's compile this code down again, but now we're going to compile it using fast math. So that allows it to use SIMD instructions, so single instruction, multiple data. So it's able to do multiple additions at the same time. Normally, it wouldn't do this by itself because it doesn't know if it's safe to do so. But we're telling it, yeah, go ahead. I don't care in what order you're adding these numbers together in this array. You can do it in any order, and you can do some of these like at the same time. And so this will give us some parallelism, and hopefully it'll be quite a bit faster. So let's benchmark that. My computer is working really hard right now. Oh, I think it's mostly Zoom. Looks like it's Zoom that's working, it's doing something. All right, so that add benchmark has been, we ran that one, and let's add the information to the dictionary. So what is our dictionary now? Okay, so you see with fast math, a little bit faster. All right. Let's do using PyCall. So PyCall allows you to call functions. Oh, I don't actually have this package added. So let me just uncomment this and run this again. PyCall lets you call Python functions. So we'll compare how fast Julia sum is to the built-in sum function in Python. Some of these times might not be very good. My computer is working, Zoom is using a lot of resources right now on my computer, so might have to take that into account and maybe run these all again at the same time under the same conditions. But anyway, I encourage you to run these on your computer as well, maybe not when you're in a Zoom call, and see what times you get. Okay, I just paused the video quickly because that was taking a while. All right, we're good to go now. Let's load up the PySum function, and then we will run PySum on this array A. And we'll check that it is giving us basically the same answer. And now let's benchmark it. I'll run this as well, and I'm gonna run this to see. Oh no, it's already doing that. So I guess I didn't need to do that, but I'll wait until it runs to delete that cell. Yeah, okay, I'm just gonna delete that cell. Yeah, so there it is now. Oh wow, okay, so Python's built-in function is actually really slow. It only ran it twice because it was so slow, so it didn't take as many samples. When it's fast, it takes many more samples to get an accurate measurement of the running time. But you know, this is pretty good. So this is in milliseconds here, and you see that it took about 2.5 seconds roughly to run that function on the array A. I forget what the length of array is. The length of A is, so it's 10 million. Yeah, 10 million. So really, people who know Python know that if you're running, doing numerical stuff in Python, that you really should be using Numpy. So Numpy is the numerical Python package. Okay, I need to apparently add this package, and I don't know if I mean, I've got Numpy on my computer, so I don't know if I actually need this conda thing. you might need to do it if you don't have Python on your computer. I'm just going to run this without doing this conda.add numpy or numpy. Not sure how to pronounce it, numpy or numpy. All right, I'm just going to pause. Yeah, so that's what I thought. I already have numpy installed. So now it's running the NumPy version of the sum function using PyImport to pull that in and let us run it. And now this is clearly much faster. So this is the way to do it in Python, as people who use Python know about to do numerical calculations. Now the NumPy one, okay, this is actually much faster now. So I might have to rerun everything again because I'm not sure if my computer is in the same kind of state for all of these tests, but that is nice to see. That is really fast. That is really fast. So if you were to just like handwrite your Py function, your Python function like this, just like the C code, this is exactly the C code, but in Python. And if we were to benchmark that, let's see what we get. I'll just run this stuff as well. Okay. So let's see. So this is the handwritten one. Okay. So actually, that's kind of surprising. I might have to run this again because the handwritten one is actually faster than Python's built-in one, which that is really surprising. But yeah, clearly you want to use Numpy to do this in Python. All right, let's do the same thing in Julia. So in Julia, we can see which function is getting called by saying at which, and this will point us to exactly the code that gets run when we run this. So let's actually click on this. This will take us over to the GitHub repository. Right here. Okay, well this is the Julia code that's doing it. It's actually defining all of these functions at the same time. I guess we'd have to dive in a little bit more in order to figure out what's going on here, but it looks like it's calling A and then it's providing the dimensions. Anyway, might have to dive in a little bit more, but the important thing to know about this sum function, it's actually written directly in Julia. So this is actually, this is not C code, whereas the Numpy one is C. So Numpy is all C, right? It's basically a way to call C code in Python, and that's why it's fast. But Julia, the Julia sum function is just written in Julia. And I guess we already ran, I thought we ran the Julia sum function above. I guess we haven't done the benchmark yet. I don't remember if we did or not. Whoa, okay, so this is amazing. So this is actually faster than Python, the Python Numpy one. So that is really impressive. Okay, so that's Julia's built-in one, written in the Julia language, not written in C. Now let's do the same thing we did with Python and C and just write a sort of a handwritten sum where we do it in the way that we think is, I mean, it actually looks just like, the Python code. Basically the same thing. Like what's the difference here? The Python, okay, so Python, you instead of function, you say def, and you have to put these colon at the end of this, and then there's no end words, right? But Julia doesn't use these colons, and instead you have to put an end, so it has to be for end and function end. So that's the difference. So let's just zoom down here again. Okay, so the handwritten one, okay. Julia's handwritten, 12. Okay, that's great. So it's 12, and compare that to Python's handwritten, it's a huge difference. So, all right. Now in Julia, we can also do like the fast math thing where we say, actually, I want you to do this loop SIMD, so single instruction, multiple data. So I'm gonna allow you to kind of do it in parallel in whatever order you feel is, that you wanna do, so that you can get even faster times. But you can only really use this if it's safe to do so. And in this case, we know it doesn't matter what order we add these up in, it's going to be approximately the same answer. Okay, so there it ran. So we see that we're getting approximately the same answer. And then let's add these times to our dictionary. So let's see what we have here. So this is the SIMD one. Wow, look at that. So this handwritten SIMD one, it's actually faster than Python Numpy. That's amazing. And it's actually basically just as fast as the Julia built-in one. So that's probably what the Julia built-in one is doing. It's just doing like a very simple for loop, but it's running it with SIMD. And that's actually faster than C with fast math, which is also SIMD. That's really amazing. All right, so let's print out the summary here. So just kind of printing it out in a nice way. I guess we're doing this RPad in order to get these different amount of dots to make it look really nice. And I guess you can also round the values to 1 digit and then again use LPad in order to make it look nice as well. So there it is. So what is the, which one is the fastest? Julia's built-in was the fastest. And then right after that was the handwritten SIMD, then Python Numpy, then C with fast math, and then C, and then handwritten but without SIMD. And then after that, there's a huge jump and we get Python's handwritten and Python's built-in. So that's kind of the story of Julia's speed. This is just a simple sum function, but there's been a lot of other similar tests like this with more complicated functions. And very often the results are similar to this, that you can actually get a very fast code just by writing things in not a complicated way. Like you don't need to know C and you don't need to really do anything tedious and complicated to get fast code. You can write high level, nice to look at code that runs very fast. Okay, so let's save this and we will close it and I'll open, I think we've got one more notebook after this, so I'll be right back. Okay, we're back. I had to switch my headphone as well because the other one was dying. So what I'm doing here is I'm charging my right headphone and I'm using the left one. So that way I always have headphones that are charged and never without my headphones. All right. And I like using these because this is actually the microphone. So that's why I like using these for Zoom calls and recording my voice. All right, so here we're going to talk about Julia's multiple dispatch, which is kind of a way to do object-oriented style of programming. And we'll see what that means. But so with object-oriented programming, you would have an X array and a Y array, and then you would do they could be different, I guess. And you could do like x.sort and y.sort. And so depending on what the object is, x or y, it's going to, call a different function, different sorting function, right? So multiple dispatch is similar to this, but instead of just looking at the type of the one object, like the x or the y, it'll actually look at the full type signature of all the arguments that are passed. And this is really nice because, sometimes you want to do different things depending on not what just the first argument is, but you want to do different things based on what the other arguments are. So we'll see how this works in Julia. So let's start by defining the simple function that we had before. So there you see that it squares numbers. And it does not make sense to pass a vector, as we saw before. So a one-dimensional array squaring a one-dimensional array doesn't make any sense. All right. So let's define a function called foo. So this is what I wanted to say, like if we have, now we're gonna have multiple inputs. And this is when you can really see multiple dispatch doing its thing. So with multiple inputs here, this function foo, we're defining it to, it has to have x and y both have to be strings. So we're sort of saying what the type of the inputs have to be in order to call this method. So if we run this on 2 strings, then it'll do its thing that we defined it to do. But if we give it integers, it'll say there's no method matching foo int, right? We didn't define that. If you look at the methods of foo, you'll see that there's just one method, and that is string. So it has to be that. Okay, so let's define it. We can use the same name, and now we get 2 methods for the same name. So if it's 2 integers, then it's going to run this function here, or this method, I guess we should really say method. So there's one function foo, but it has multiple methods. So if it's 2 integers, it'll run this method, and if it's 2 strings, then it will run this code up here, right? So now we can see if we say foo of 3, 4, now it's fine because we have a method for that defined, right? So that's a simple example of a function with 2 methods. So in Julia, actually, there's some functions that have a lot of methods. So for example, the plus, really it depends on what the things that you're adding are. And there's 184 different methods defined for plus, and they're in a variety of different places. GMP is the multiple precision library to allow you to use big integers and big floats and so on. Yeah, so they're all over the place. You can see all the different, you can add dates. You can deal with complex numbers and a lot of functions. So maybe I won't scroll through the whole thing, but you can see that plus has a lot of different methods. And so when you call plus, it's actually going to go through this list in some way. I'm not sure exactly how it does it. And it'll find the method, which is the most specific method for the types of objects that you're calling it on. And of course, you can always use the @which to tell you which method would be called if I call the function in this way. So for example, if you say @which 3.0 and 3.0, so these are both float 64. So it knows that it's going to call the function where x and y are both float 64. And this is going to be exactly this code here. And again, you can click on this and it will take you to the source code in GitHub for that function. And I guess it's calling add float xy, which, let me just see if I can find this, add float. It must be defined somewhere else. Anyway, I don't want to, you can, some of these rabbit holes can go quite deep. All right, so let's look at what happens when you call plus on two floats. So we can actually get the LLVM code for this, and it looks like this. So I guess that's, you know, unless you know LLVM, which I don't really. I guess the point is the LLVM code is quite terse. It's very, very short, right? And there's some other @code functions that we can look at here. Let's see. So @code. Let's see. I wonder which one. Anyway, I guess the one that's most interesting is at this point is the @code native. So @code native will actually. I guess LLVM has a way to look at a binary that it generated and sort of extract what the machine instructions are, and then print that in some, you know, nice way for humans to look at. But, you know, reading machine code I'm not familiar with this, but there's the add function. I believe these are registers in the CPU. So it's adding these two registers and it's storing the result in this register, so for example. Okay. So let's define a function called myAdd, and let's look at what happens when we look at the LLVM code for myAdd, and it's exactly the same. So so that's the way it works. I guess we could look at this code typed myAdd. So it knows that these things are floats, so it's calling the add float function, and it knows that the result of adding those is going to be a float 64. If I change these to integers, now it's going to use the add int function, and the results will be an int 64. And I'm just a little curious what happens if we do a mixture of the two. So if we do a float and then an integer, then actually I'm not sure what this is. I'm not sure what that stands for. But it looks like it's converting the integer into a float 64, and then it's adding that to the x, right? And I suppose if we do it the other way around, then it will first convert x into a float and then add that to y. So what it's doing, I know what this is called. It's this promotion. So whenever you give it two numbers of different types, it will promote them. It'll promote them to be the same type, and then it'll perform the operation that way. So that's what's going on here. This is this promotion operation. Yeah, I think there's a function called promote, and this is what's used in order to determine the common type. Yeah, so if you say promote an 8-bit integer, a 16-bit float, and a 32-bit float, the most general of them is going to be, or I guess the one, so these, yeah, so the most general would be the float 32. So so there, all of these numbers then are converted into float 32, which are written like this with these f's. So these f's will give a float 32. So if I was to just do like 1.0 e minus 4, the type of that is going to be a float 64. And if I want it as a float 32, so use just 32 bits instead of 64 bits, I can do 1.0 f minus 4. And that will give me a float 32 number. So yeah. we'll get into this some more, but I just thought I'd mention that here. So I think that's the end of the video now. We have now gone through all of the notebooks in this short version of the tutorial, and according to my timer, it's been more than 2 hours. So I hope you enjoy this. We'll be able to now move on in the class and do some other things. I think next class, it would be nice for us to learn how to use Git and GitHub. So we'll do that. And then we'll be getting into the floating point arithmetic material very soon. Okay, so I'm just going to, I like to quit my Jupyter notebook rather than just closing it. So I quit that, and then if I refresh, you'll see that it's closed. So the server is done. All right, so let's stop there, and thanks for watching.